Ask a Python program to multiply 5 by 3, and it might print 33333 instead of 15. That bug comes from one fact about reading user input. Today we make programs interactive, run one step of Newton's method, and format output cleanly with f-strings. To read data from the user, call the input function. Give it a prompt string and save the result into a variable. Here, text is set to input with the prompt type anything. When Python reaches the input call, it displays the prompt on the shell and waits. The program pauses until the user types something and presses enter. Think of input as an expression that gets replaced by whatever the user typed, always stored as a string. If the user types howdy, the first line becomes equivalent to setting text to the string howdy. The second line prints 5 times text, which repeats the string 5 times with no spaces in between. Howdy, 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 howdy. This string behavior matters even when you ask for a number. Here, num1 is set to input with the prompt type a number, and then we print 5 times num1. If the user types 3, Python stores the string 3, not the integer 3. The quotes are invisible at the keyboard, but they're there in memory. Multiplying a string by 5 repeats it. So the output is 33333, the digit repeated 5 times. The program didn't misbehave. It did exactly what string multiplication means. The misconception is assuming Python knows you meant a number. To do real arithmetic, cast the input. Wrap the entire input call in the conversion to integer. Now num2 is set to converting the input to an integer. The user string 3 becomes the integer 3, so 5 times num2 performs genuine multiplication and prints 15. Use the integer conversion for whole numbers and the float conversion when decimals are expected. The pattern to remember: read as a string, convert immediately, then compute. That one wrapper is the difference between 33333 and 15. Combining input and output creates an interactive program. This one asks for a verb and a response. First, verb is set to the input with prompt type a verb. Then we print the words I can, the verb, and better than you, separated by commas inside the print call. Finally, we print the verb plus a space, all multiplied by 5. If the user enters run, the first print produces I can run better than you, and the second prints run, 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 run. One detail: multiplying verb plus a space by 5 leaves a trailing space after the last word. A worthwhile refinement is adjusting that final print so the last repetition drops it. These same input and output ideas drive a mathematical example. Newton's method finds the roots of a polynomial through successive approximation. Start with a guess, refine it, then repeat. The full algorithm needs loops we haven't covered yet, but we can write its core step, computing a better guess from a current guess. Here is the update rule. The next guess equals the current guess minus f of the guess divided by f prime of the guess. Python doesn't evaluate functions or derivatives symbolically, so we hardcode both. To find the cube root of x, the function is f of g equals g cubed minus x, and its derivative is 3g squared. Substituting these into the update rule, the next guess equals g minus the quantity g cubed minus x, all divided by 3g squared. Here's the program. X is set to converting the input to an integer. With the prompt, find the cube root of. G is set to converting a second input to a float. With the prompt, starting guess. Both casts matter because the next lines do arithmetic. We print the current estimate cubed, which is g to the power of 3. Then next guess is set to g minus the quantity g cubed minus x, divided by 3 times g squared. Finally, we print the next guess to try. Run it for the cube root of 27, starting from a guess of 5. 5 cubed is 125, far too large. The update computes 5 minus the quantity 125 minus 27, divided by 3 times 25. That's 5 minus 98 over 75, about 3.69. One refinement step, much closer to the true answer of 3. Repeating it automatically requires loops, which come later. Now output formatting. Building output by passing comma-separated values to print works, but commas insert a space between every item. Try placing a percentage right next to its percent sign. The comma forces an awkward gap, like 3.0 space percent. The older workaround is casting each number to a string and concatenating the pieces by hand, which gets tedious fast. Since Python 3.6, F-strings solve this in one step. No casting, no concatenation. Prefix the string with the letter F and place any expression inside curly braces directly in the text. Here's an F-string in action. Number is set to 200. Fraction is set to 0.03. Then we print the F-string. In braces, number times fraction. Then the literal words is, then in braces, fraction times 100. Immediately followed by a percent sign, then of, then number in braces. Everything outside the braces prints literally. Everything inside the braces is a Python expression. Python evaluates it before inserting the result into the text. So the output reads, 6.0 is 3.0% of 200, with the percent sign tied against the number. No casting needed, no concatenation. When you have a choice, prefer F-strings. 3 tools, 1 sim. Input pauses your program and hands back whatever the user typed, always as a string, so cast with the integer or float conversion before doing arithmetic. Combining input and output makes programs interactive, enough to run one full step of Newton's method. And F-strings embed evaluated expressions directly inside text. The broader lesson, expressions can go almost anywhere. Inside an index, inside a print call, inside an F-strings braces. Python evaluates them in place and moves on. That versatility is one of the language's real strengths.